Hello, everybody, and welcome to Optimizing Request Unit Consumption. Welcome to the Azure Cosmos DB Conf. Really excited about this event and really happy that you're joining me virtually. My name is Warren Chavez, and allow me to introduce myself. I've been a DBA and consultant for 14 years. I used to work at HP in Costa Rica. Now I work at Pythian, based out of Ottawa, Ontario, in Canada. I am very honored to be a Microsoft Data Platform MVP. Feel free to reach out to me on Twitter at warchav and check out my website, createdatapros.com. And if you have any questions after you watch this session, you want to shoot me an email to get something going that way, you can also reach out at Warner at createdatapros.com. So the agenda for today, main objective is we're going to cover the different consumption models and configs and practices that you can use to optimize how many request units you consume. If you are not super familiar with Cosmos DB, we are going to go into what the request units actually are. So you're still going to get value out of this session anyway. So we're going to cover request units, going to cover all the different configs, and of course, we're going to be showing a lot of demos so you can see the actual impact and how the things work when you're actually doing stuff in practice. So first of all, what are request units? Well, request unit defines how much of the system resources are consumed by a particular operation in Cosmos DB. Keep in mind, Cosmos DB is a platform as a service offering. You don't have to manage the underlying hardware operating system or the software that runs the Cosmos DB engine. So instead of provisioning a specific amount of cores or memory or IOPS, you just have to say how many request units you want. And each operation that you make has a certain request unit cost. So basically, your throughput of your entire Cosmos DB database is defined by request units per second. Another thing you need to understand is that the operations consume a deterministic amount of request units. That means that if your operation stays the same and your data stays the same, then your request unit cost for that particular operation will stay the same as well. And then RUs can be provisioned in two different ways. They can be done per container, and I'll go in a second a little bit deeper about what the container is, or they can be provisioned at the database level. And when they are at the database level, they can be shared by the different containers. RU consumption is driven by your consumption model, and we will dig deeper on that as well. It's driven by the item size. So if you are writing bigger items, for example, is driven by the container size. As your data gets bigger, some queries might depend on the size of your data. For example, if you're doing orders, data consistency, this is a very interesting bit that actually has impact on RUs and is very easy to tweak and get an optimum RU consumption, and we will go in detail on that as well. The indexing policy, you can manipulate this as well to make it more or less expensive for RUs. And of course, the more complex your queries are, the more RUs they'll consume. And I'll just give some quick tips here on the slides and in the demos so that you can get started consuming less RUs with your queries as well. So what is the container? As I mentioned before, request units can be specified at the container level or the database level. At the container level, what we think about is that Cosmos DB is a multi-model database, and you've probably know this, and if you don't, then what that means is that you can talk to Cosmos DB using different type of database models, like the document model that you use SQL to query, like a graph. You can talk to it like a table that has key value pairs. Since not all of these models have the same concept of table or graph or collection, then we can use the general term of container. Behind the scenes, these containers provide unlimited scale by dividing into multiple partitions that can be assigned to multiple nodes. And the beauty of this system is that you don't have to manage any of this on your own. All you have to do is provide a partitioning key and manage your request units, and Cosmos DB under the scenes will distribute your data and make sure that you have enough resources for your requests. So the hierarchy goes this way. The databases have containers. The containers hold the data records. And those data records, depending on the model that you're using, can be documents, they could be rows, they could be nodes in a graph, and so on. Okay, so now that we're going to get started talking specifically about request units, the first thing that we need to explore is what request unit consumption model should we choose? And we're going to go over the options, and then at the end, we're going to jump into the first demo. So first thing is that now Cosmos DB is offering a serverless offering. So you have the option of doing serverless, which is in preview right now, or provision throughput, which means that you give it a more specific amount of request units, and you're always paying for that amount of request units. Serverless only bills exactly for the RUs that you consume when you connect to the service, you shoot a query, or you insert a record. Now, that sounds great on the surface, right? But actually, if you run a 24/7, 365 workload, serverless will end up being more expensive. In that case, it's better to just do provision throughput. The idea for serverless is to use it on either non-production workloads, like for example, if you're doing dev or test, you're obviously not going to be running 24/7, 365, or if you're doing low peak traffic workloads that sometimes in the day you get some queries and then it goes down for several hours and you get no activity at all, right? That is the sweet spot for serverless. Keep in mind as well, serverless is not exactly functionally equivalent to a container or a database that has provision throughput. Serverless is constrained to a single region, and your collections can be a max of 50 gigabytes, okay? Now, if the workload is 24/7, as I mentioned, with an expectation that you're gonna get a uniform response every single time, then provision throughput is your best option. But as I said before, there are many workloads out there, either non-prod or production workloads that don't have constant throughput requirements that could be well served with serverless. So that's the first decision you have to make, right? And keep in mind, at the same time, if you are running a real production 24/7, then provision throughput might be best for you. Second, we have the choice of whether we do container request units or we do database request units, right? So database request units will share the request units amongst all the containers inside of it. So that allows you to share resources and not waste as many request units, right? However, the container level might be best if your request unit capacity has to be guaranteed for application SLA. Database level is best when you have multiple containers that have some ebb and flow during the day. Some of them will spike at different times than the others. If all your containers are going to be spiking at the same time, then the idea of database RUs does not have as much benefit. For example, if we look at the screen right now, we have the activity for one container. Then we can see, right, they will start to slow during the day. Let's say it peaks about half day and then it goes down. And so we have, if we have provision throughput static at the container level, then we will have quite a bit of capacity that we're not utilizing, right? And then we utilize it at the middle of the day, and that's when we consume most of our use, and then it will go down, right? Now, if we had this for many containers, we can see that if they move differently during the day, then that unused capacity gets smaller, right? So that's what you want to do if you want to have database level RUs. If you have multiple containers that are not spiking at the same time, that is the key piece, because otherwise you will just consume all the resources in the database as well. And we'll get into a little bit on that, what can you do about it, in a second, okay? But just keep in mind, multiple containers, if they have different spiky patterns, you can actually use database level RUs. And so we come to the last bit about the consumption model, which is, do you use auto-scale or should you use manual? And this goes hand in hand with what I just mentioned about being able to service your workload and maintain your SLA. Auto-scale allows you to set a max RU value And then your resources will fluctuate from 10% of that max to the max value. For example, on the screen, I have 400 RUs to 4,000 RUs, right? So you're allowed to fluctuate in that range. Now, if that max in the example, for example, is 4,000, is used 66% of the time or less, then you actually spend less by using autoscale than by setting the manual RUs at the Tmax level. For example, let's think about a workload that only requires those 4,000 RUs during a couple of hours of the day, and then it goes right back down, right? In that case, it's an excellent use case for autoscale, because the alternative to deal with those spikes would be to have a collection that is mostly idle during that time. Or it would be to have, again, a database where you have lots of containers trying to share those RUs, which is also gets harder to exactly manage and make sure that you don't run out. So on highly variable workloads, autoscale helps keep idle request units to a minimum. You're using less unused capacity as your workload changes. In my opinion, if you're running a production workload and you are okay with the cost variability, then you should always have auto scale on, because this is, again, just my opinion. But for the most part, what I see is that most clients would rather just have cost variability that you can cap, right, by using that Tmax value, than to have unexpected exceptions and SLA issues with your application because you simply hit an unexpected ceiling with your request units. Okay? So let's see, for example, in this example, let's say we start a collection at 400 RUs, and then as our workload progresses during the day and gets busier, the system automatically pushes us into the 600 RU level. And as it continuously gets busier, the system pushes us into the 1000 RU level. And then we go back down to 600 RUs again as the usage goes down after we go through that midday peak, right? And the beauty, again, of this system that the team has implemented is that you don't have to manage the movement through those phases. You only have to say, this is the min, this is the max, and you let the system ebb and flow automatically as your workload fluctuates as well, okay? So let's take the first demo break. Let's check it out. I'm going to show you the different configs there in the portal, and we'll look at a couple of databases. I have a utility that we can look at this in action. So let me switch out. So I have this VM right here. This is my Azure portal, and I'm just going to show real quick here how you can create and decide whether you want to do serverless or provision throughput. Right now, you just have to create a new account. And then when you create a new account, you get the option. You see it right here on the screen. It says provision throughput or serverless. As I mentioned right now, at the moment of recording, serverless is in preview. If you do decide you want to go for serverless, that's it. You can go ahead and create it. Now, I'm not going to create this one. I already have several created. So I'll just show you real quick. If you create one that's provision throughput, you can see right here in the overview, you'll be able to see provision throughput. If you created a serverless one, in the overview, in the capacity mode, it will say serverless. Now, serverless, as I mentioned, is in preview, and you currently cannot switch back and forth between the different consumption models. Now, let me go into the Azure Cosmos DB account that I'm going to use in this case to show you the next thing, which is the provision throughput. If you look at my provision throughput here for this particular account, I have one collection that has 400 throughputs that are used, that are static. And you can see I have two collections called Trending Artists from a database called Music Service. This database is shared, right? So you can see I have 400 RUs in this database that they are shared by these two different collections, Trending Artists and Trending Artists 2. Okay, so that's how you have this. You can switch this if you wanted to. I can go into this one in particular. Let me open this up. I'm going to find it here. And you can see if I go to scale, right, I have here manually right now set to the 400 shared in this database. Okay, so let's see how that works in practice. I have a utility here that I use. I'm going to be connecting to both of them at the same time. In this utility that I wrote, I'm just using the Cosmos DB SDK, and I basically set an amount of artists. Again, we're going to pretend it's a music service, and we are keeping track of how many listeners are listening to a particular artist, right? So I set an amount of artists, calls per second, and then iterations, right? And if you see right here, I'm connected to that CDemos Cosmos database, and my collection is this trending artists. Now, if I switch to my other window, you'll see I have the same config, but I'm using a different collection, right? In this case, it's trending artists too. And this allows me to just do real quick. I can do a write workload. I can do the same thing on the other side, start a write workload if I wanted to, right? Okay, so now let's see what happens if we run something beefier. That was just one artist, right? But I can reset this and then set something like I want 20 artists at the same time with 30 calls per second, and we're just gonna do 10 seconds. And then I'm gonna run this workload again. As you can see with my utility as well, we'll be able to see how many request units we are consuming as the workload runs. So we'll just let this run. This should take about 10 seconds or so. And it should be close to being over now. And you can see successful calls, 528, the average throughput, and we had no exceptions running this. So right now, remember, this is a 400 RU database. So these two collections are sharing those 400 RU. So what happens if we reset this other one and we set it to the same value? So let's say we do 20 artists, 30 calls per second, and 10 iterations as well. And then what we're going to do is we're going to start both of these at the same time, and we'll be able to see how that affects throughput because they are sharing their resources, right? So let's wait for them to go. As you can see now, they're both going in parallel. Now, this is not the ideal case for using database, right? Because both of these collections right now, because I'm pushing this workload, it would be similar to saying that they're spiking at the same time, right? And that affects the throughput as well as we would expect, right? Now, let's wait for this to go down. And we can see here the decrease in throughput, 491 in one side, 526 on the other. So we were not able to get as much when both of them are running at the same time, right? But that's expected because they are sharing resources. Now what we can do is we can even bump this up higher. Let's see, for example, let's do a reset and set to 30 artists, 30 calls per second, 10 iterations. Let's set this higher, reset, 30 artists, 30 calls per second, iterations. And we can run the test again. Start right. And again, this should only take about a little bit over 10 seconds to run. And we can see now that I increased the throughput or the requirements of the workload that I was trying to run. It is actually visibly slower, how they're both processing and going through that queue of requests that I've created. But it still should be done in just a couple of seconds now. All right, and now we can see here, we have actual exceptions thrown by Cosmos DB, right? So basically, the SDK gives you the option to do automatic retrying of calls, but I turned it off so that I could show the behavior here. We can see in this particular workload now, the system has denied some requests because it ran out of resources, right? On this test on this side, it did 19 times it did that. On this side, 22 times it did that out of 700 or so calls, right? So once we actually increase the workload even more, now we are literally out of resources. Now remember what I mentioned before is that, in my opinion, it's better to have the cost variability than to be producing exceptions for your clients. So we can do now is go back into this same collection, and if you see here, I have the option of enabling auto scale. So I'm just going to enable auto scale. Go ahead and press save. And that should just take a few seconds to complete. And what this does behind the covers is that I don't have to reconnect the system. You guys can see I have my two utilities still open. Now autoscale is enabled, and we're just going to go ahead and rerun this workload right now. So let me just set it up. And we can go ahead, rerun the workload, and we'll see what happens now. As you can see now, it has increased actually the speed visibly compared to the last time that we run it, running both of the workloads. And it should be done in just a few seconds. And it's almost done now. And you can see the difference here, right? I enabled auto scale on the portal. It took a few seconds to get enabled. And then immediately after we run the same utility, I did not have to restart it, do anything about it. And now we have 0 exceptions for both of the tests, right? Because automatically the system, instead of giving me the messages of saying, hey, I have to deny your request because you ran out of resources, it simply gives me more request units behind the scenes, and I don't have to throw exceptions to my clients. All right, so that is the consumption models, and I hope that's a good demo showing the benefit there of the auto scale and how it works, how transparent it can also be for your system. Now, what else affects request units? Well, consistency actually is something that has a direct impact, and I find really interesting. A lot of people don't realize this, and they don't realize how much flexibility Cosmos DB has in this regard. Cosmos DB gives you options of consistency models, going all the way from the one that offers the most fidelity but gives you higher latency and less availability, to the ones that offer less fidelity with lower latency and more availability. Now, I'm not going to go into each one of these in detail. The Cosmos DB documentation has lots of good information about it, but just so that we are all on the same page, these go from strong, bounded staleness, and then after bounded staleness, you get a request unit discount. Session, consistent prefix, and eventual consistency all consume less request units than strong or bounded staleness. So this is a really easy way to get a benefit on decreasing your request units. So bounded staleness and strong, as I mentioned, consume about double the request units of the other consistency models. So because these are more expensive, you should really verify that you need them before using them. Otherwise, you might be consuming double the RUs for these operations when you don't actually need that type of stronger consistency. Most clients use the session consistency, which basically says that you will be able to immediately read your own writes in your own session. And keep in mind, consistency can be at that container level. It can be at the client level. You can even override it with the SDK at the specific request level. So you have lots of flexibility to really make sure that you're using the consistency level that you need for your specific operation. So let's check that out as well real quick. So let me close out one of the utilities, and I'll just show it real quick in this utility. So let me reset this, and just so we see it with lots of clarity, I'm going to pick one artist, and we're going to do maybe just 1 call per second and 5 times. And we're going to start a workload. And now, if we look at the status here, where you can see the consistency level that I'm using in my utility by the default is the bounded staleness. But I can go ahead and change it to session. So let's do that. Let's change to session. Let's rerun the workload. All right, and let me just scroll up a little bit, and you can see right away, right at the top, it was when we had bounded staleness. Every single read there of that query was 5.58 request units. After I switch it to session, immediately I get the discount down to 2.79 request units. So for an operation that doesn't require the bounded staleness or the strong consistency model, you can immediately get a discount right away by using some of the other consistency models instead. So that's very easy to tune and tweak as well at different levels. And this is an immediate effect down in your request units, right? Let's go back. Let's see what else do we have. Query complexity as well, obviously, is something that impacts. We can have some query best practices. For example, you can use the ID. You should always use either an ID or an indexed field for your predicate. Then you should also try to avoid cross-partition queries, and we're going to talk about that a little bit further on today, because usually what I've seen is that people try to do somewhat analytical type of queries using the Cosmos DB connection, and this causes cross-partition queries and a lot of RU consumption. And now we have a really good alternative with the Synapse link to avoid that. And I'll go into Synapse link in detail in just a few minutes. And then one of the latest improvements that's really big that the Cosmos DB team has done is that we have the option to create composite indexes. So you should use them absolutely if they are needed for your queries so that you get the benefits there of a lot of RU diminishing consumption because you're using a composite index, right? So as long as the benefits from your queries outweigh the cost of the new index, then you are good to go, right? So let's check it out as well. Let me jump back into the VM, and I have the Cosmos Explorer here. And just to give you an idea how to work with this, if you're not familiar with this, you can run a query here in the Cosmos Explorer. I'm just going to execute this query, which is a basic select top 1 star. And in the query stats underneath, you will see you get the request charge, and that's the cost. So this is a really easy way for you to tweak and tune and look at how many RUs you're consuming. You can simply copy paste some queries here, play around with them, deconstruct them, modify them, and see how it impacts your RU consumption, right? If you are doing point lookups, for example, I have two queries here at the top. One, we are selecting directly from their ID, and then the other one is basically the same as this record, but instead of going directly to the ID, is using different properties to find this specific record. Now, obviously, the ID path is going to be more direct because it's just the ID exactly. So we can run this, and we'll see the impact on RUs as well. So we can see the ID path just going directly to that property is 5.66 RUs. This other case, we are actually going to return the exact same record, but we're doing it through the different indexes by just applying more filters, and we get a slightly higher 6.06 RUs. Now, in absolute values, this is not a huge difference. It's 0.6 RUs, but in the range is actually about a 10 to 15% discount by specifying the specific ID, right? And if we think about running a workload that has thousands of calls per second potentially, then these gains compound, right? So benefit here is if you can use the ID to find a specific record or document, depending on your model, then you should use it, right? Now, just like this is a thing that works in Cosmos the same as it works in other RDBMSs, for example. And it is to make sure that Cosmos can search the indexes, right? For example, here I have a select top where the artist name like and the wildcard is at the end. So this will actually work well and it uses the index, and we look at the value here, 6.42 RUs. Now here, this is another practice that is commonly brought up when people talk about tuning SQL in general with RDBMS engines, never mind just a NoSQL one. And it is to people applying a filter on something that has a function on a particular column, right? So for example, here, we're doing, okay, well, instead of doing a like, we're doing a starts with a lower of the artist name. So in this case, the lower function is going to make it so that it is not searchable through the index anymore, right? And we'll wait for that to execute. And we can see it already is visibly slower. And we can see the massive difference in RU consumption, right? So we went from a few RUs to 24,000 RUs, right? So no comparison at all in this case. And then here we have, you can look at this one that I just ran with 24,000 RUs, but I'm going to do something similar, but instead of saying it starts with and lower, I'm using the built-in capability of the starts with function to be able to do case insensitivity search so that I don't have to apply this lower function, right? So it's using the built-in capability of the starts with function instead, and we go back to a very low 25 RU consumption level. Okay, so that's something very important. It applies to every single database. Don't do something that invalidates the searchability of your predicates, okay? And then finally, with this new capability of composite indexes, then you can run new things and new capabilities. Like for example, you can do an order by on multiple fields. If you look at this query that I have here, I have a where clause that I'm passing in a wildcard, and I have an order by the artist name and how many listen, and the timestamp of the last time that we measured how many people are listening, okay? If I run this select query now, you'll see here I actually get an error, and it says that this order by query doesn't have a composite index that it can be served from. So in this case, it's not only that we're going to get lower RU consumption by getting by using a composite index, but it's actually required for this type of query to do it. Now I'm just going to go here and do a new SQL query, and I actually already have a composite index on this trending artists too. Okay, so I created it in this other one so we could see it side by side right away. And I'm just going to run it. And you can see we get it, boom, immediately right away. 13 RUs consumed. We're doing a filter wildcard and both two feature order by. To do this is very simple. If we go back into the portal, I'll show you the trending artists. And if we go here into the settings, if I go to indexing policy, you can see now there's a support for this new section of the indexing policy called composite indexes, where I created this new index that is artist name ascending and artist listen count timestamp descending. And this composite index, again, not only does it provide benefits because of less RU consumption, but it outright enables capabilities such as ordering by at the same time with both of these two fields. Okay. All right, so let's go back. Let's see what else do we have here. The indexing policy also has an impact, of course, in RU consumption. So all properties are indexed by default, and this might be too expensive for you if you're not really using all the properties to do a predicates on the where clauses. Then you don't really need to index all of them. Now, indexing all of them then, of course, has a specific effect on space and request unit consumption. There are different types of indexes as well. There's hash indexes, range indexes, spatial indexes. They can be updated in a consistent way. So as soon as you change the document or the collection, then the index updates. Or you can actually disable and say you don't want it to update it at all. Or there was also a way to update it called lazy, which would do it asynchronously, but that has been deprecated at this point and is not going to be available anymore. But you might still see it in old blog posts and things like that. And there's two ways to handle the indexing. The automatic, so every time that you update the underlying data, it gets added to the index. Or there's also a way to do it manually, which means that only some particular records or documents, with using the SDK, you can set them to be indexed specifically. Now, I honestly just use the automatic mode, and with the consistent behavior. However, what I do a lot is to help my applications tweak the amount of properties that are indexed by default, because that, again, does have a direct impact on consumption. And whenever you do an indexing change, keep in mind, Cosmos DB does this online. You specify the new indexing policy that you want. The system continues to use the old policy until the new policy is in place, and then it switches it behind the scenes without any disruption. The only thing to keep in mind is that the read queries are going to be eventually consistent while that transformation is happening. All right, so let's check that out as well. Let's jump back into my utility here. And we're going to do something really simple here. So I have this workload set up. I can do a start write. And here we're just doing several writes of this particular artist for 5 seconds. So we can see I consumed 16 request units. And right now, if you look at the indexing policy that I'm using for this particular collection, I am indexing every single field, right? I have the included paths set to star, and I also have a composite index. Now, for demo purposes, I'm going to go ahead and just get rid of all this so that basically there is no more automatic indexing anymore. So let me go ahead, move this to false, and I'll set this to manual so we can see the full impact of just getting rid of the indexing completely. Okay. Click save. Let's see. Requested value. Oh, wait, I put the wrong thing here. I put manual. I should. It's none. So I put the wrong thing. 1 second. So automatic. Move it back to false. And here it's none. All right, that's going to take a little bit to update the indexing policy. And like I said, this happens behind the scenes. It's updated now. Go back to my container. We'll start the workload again. And we can see immediately I get right away a smaller charge in request units, right? Again, for demo purposes, I basically disabled all indexing so I could show you the maximum impact, but this still has an impact that compounds if you tweak it to only the fields that you are interested in, right? So maybe we wouldn't have a discount of 16 to 9.9, but we could have seen a discount of 16 to 12, for example. And once you think about every time that you're writing, you get that discount over and over and over, you're looking at 15 to 20% discount on your entire workload request unit consumption, okay? So it is worth it, absolutely. All right. And then finally, the last topic I wanted to cover is what to do about analytical queries. And here, the thing to realize is that the Cosmos DB engine itself is not really optimized for analytical workloads, but the data that you're storing there likely has lots of potential for analysis. Now, if you were to think about what usually analytical queries do, they usually scan the big portions of a data set and they usually aggregate over it. So that means that if you run it on a Cosmos DB engine, it would be cross-query partitioning, it would be scanning the collection, it would drain your RUs very quickly. Microsoft has introduced something really cool called a Synapse link. And this is a way that basically protects your Cosmos DB are used by doing all your analytics from Synapse Analytics. So this is very, very cool because all the compute is spent on the Synapse side and does not impact your Cosmos DB RUs at all. In order to do this, when you create the collection, you enable what is known as the analytical store, and the analytical store behind the scenes runs a process that switches Cosmos DB's transactional format automatically into a columnar format and provides access to it from Synapse Analytics. And this, all you need to do is enable it, and all the behind the scenes magic happens automatically for you. There's no RUs consumed on the Cosmos side at all when you run queries through the Cosmos Synapse link. And I can't stress this enough. If you were thinking, how do I run reports and not impact my Cosmos DB application because this data, I like it, and previously maybe you were developing ETL or something like that, the Synapse link provides a great solution for all these issues. Immediately, you don't have to do ETL. You simply query your Cosmos DB data, and you're consuming the compute on the Synapse side, not on the Cosmos DB side. So real quick, I'm going to show you how that works. On my side, I got Synapse running already, and I'll show you how simple this is to set up. So I'm going to use the serverless pool in Synapse, and you just have to create a credential and you pass in the secret for your Cosmos DB database. Once that credential is saved in your database, then you can run an open row set query. You just say the provider is Cosmos DB, this is the connection data, this is the credential that you need to use, and this is the schema that I want to use for this particular query. Because remember, Cosmos DB, of course, is a NoSQL database. It might have a more complex schema than just a regular table with normalized fields, but you can specify that as well. And in this case, what I'm doing too is, for example, this is a pattern that I've been using now, is that I create views on top of my Cosmos Synapse links so that this configuration information is abstracted away from the consumers of my views, whether they're DB developers, they might be analysts, data scientists, etc. So they don't have to be setting up this configuration. I set it up for them. I give them access to the view, and boom, that's all you need to do. And then, for example, once that is all set up, look how simple it is. I just do, for example, a select distinct artist name from the Cosmos trending artists and order by artist name ascending. So basically, all the artists that are trending right now in all the different records that are writing into the Cosmos DB, a select distinct of all of them could be scanning all the partitions just to be able to find all the different ones. In this case, I just have to run this, and it runs as an analytical query against the analytical store. And right now it's running here against the SQL serverless pool. The nice thing about this, as I mentioned before, is this compute that is taken right now to go over my collection is being consumed on the Synapse side. You can see I got my answer now. I got a bunch of different artists, all the distinct list of all the different artists in my collection. And I produced no impact at all to the request units of my Cosmos DB collection. All the compute was consumed on the Synapse serverless engine instead. All right. All right, so recap. Well, we covered a lot in this session. I hope that you're gonna go away with lots of good bits and value here. So request units, they control the throughput of your Cosmos DB database, and now we have lots of flexibility in terms of how we consume and we provision those request units. They can be serverless, or we can be provision throughput. We can manually set it to a fixed value, or we can leverage autoscale, and we can also choose between having them at the specific container level or shared by different containers that belong to the same database. And then once we've decided on the optimal consumption model, we can further tune them by adjusting the consistency level, the indexing policy, the queries. And if we are looking at the use case of running an analytical workload on your Cosmos DB data, then the Synapse link allows you to run a full-blown analytical workload on your Cosmos DB data with no ETL and with zero impact on your RU consumption. So again, thanks for joining me today. Thanks for watching, and I hope you have a great time trying out some of these tips and tricks on your Cosmos DB database.